Hello everyone, hopefully you're doing well. In this video, we're going to continue with chapter 4. Okay, so we're gonna start with section 4.3. Section 4.3, because if you had a chance, I'm hoping you already reviewed chapter section 4.1 and 4.2, 4.1, where we talked about some basic concept of probability, section 4.2, addition, rule, and multiplications, and in section 4.3, we're going to continue reviewing complements, conditional probability. Very important so far. Those are some very few concepts. If for some reasons you miss it, I strongly advise you to go back and watch the first two videos. But in this one, we're going to compute the probability of at least one occurrence of an event A. We're going to apply the multiplication rule by computing the probability of some event, and given that some other event has already happened. So that's what we're going to do in these sections. As key concepts, we're going to in part one, of course, of this section, we extend the use of the multiplication rule to include the probability that among several trials, we get at least one of some specified events. So we consider conditional probability. I'll buy you pizza, okay? I'll buy you pizza given that, you know, Barcelona team win. I buy you pizza given that Patriots win. So we're gonna do it with conditions, right? And for some of you already did some couple of truth tables, you would see. But in second part, we would consider conditional probability. The probability of an event occurring when we have additional information that some other event has already occurred. So we're gonna do that, of course, in part three, if we have time, of course, we would provide a brief introduction to Bayes' theorem. But let's do it very quick about complement rules. We said that complements the probability of at least one. All right. So when finding the probability of some event occurring at least once, so we should understand this. At least once mean one or more. Okay. So complement of getting at least one particular event, is that you get no occurrence of that event. So very important. For example, let's say not getting at least one girl in 10 births is the same as getting no girls, which is also the same as getting 10 boys, right? Not getting at least one girl in 10 births is the same as getting no girls, which is also the same as getting 10 boys out of 10 births, right? Not getting at least one girl in 10 births, getting no girls, or getting 10 boys. They are all the same. So that's at some point what we are going to explain in this, right? So for us, these steps describe the details of finding the probability of getting at least one of some event, right? At least one of some event. Let's A, getting at least one of some event. And probability of not A or not A. Remember, if you have that's event A, let's say event A. If we call this one event A, now not A. Okay, so that means A is not occurring, right? So we put it a bar on top of the A to say getting none of the event being considered. So finding probability of A, to find a probability of not A. I'm sorry for that. I'm sorry. Sorry for that. So for not finding the probability of not A, for example, probability that event A does not occur. This is relatively easy using the multiplication rule. Okay. Now, for step 4, we said subtract the result from, and that means which, look, if I have probability of A plus probability of not A, that should give you 100%. So let's say if you have $100, you give your sibling $30, how much you have left? 70. So that means what you give to your sibling plus what you don't give to your sibling must be equal to the whole. To the total, right? So if you give $30 to your sibling, that means out of your $100, there are 70 you didn't give to your sibling. So that make it $100. So that means it's A plus not A give you the total, right? A plus not A give you the total. So what you give plus what you don't give, you don't know. Now, if I want to know, if I know what I don't give, then I can subtract it from 1 to find the probability of what I give. If I don't know, if I want to find out what I don't give, I can subtract it from what I give from the 100%. So we can do either ones, and that's what we show you here. Probability at least one occurrence of event A equal 1 minus probability no occurrence of event A. Let's go very quick with a few examples. So we're gonna review them very quick and see what happened with these. Okay. Let's say for the first one, find the probability that when a couple has 4 children, at least one of them is a girl. Okay. So in order to find, probability that, at least one of them is a girl. So let's say at least one of them is a girl. Probability that the first one is a girl, what's gonna happen? Yeah, 1 out of 2 because you either have a boys or a girls, right? And the second one, probability that it's a because you have 4 children. Remember, you have 4 children. That you have 4 children. Okay, children 1, children 2, and children 3, and children 4. Right? Probability that the first one is a girl. Remember, at least one girl, right? At least one girl. The probability that the first one is a girl is what? Yes, 1 out of 2 because it's a boy or girls. Probability the second one is a girl, again, 1 out of 2. Probability the third one is a girl, 1 out of 2. Probability the third one is a girl, 1 out of 2. Now, remember multiplication rule? You can take that's would be probability it's a girl would be 1 out of 2 times 1 by 2 times 1 times 2 times 1 times 2, and you can say it is that one would be what exactly would be 1 out of 16, if I understand pretty well. Now, look, this is the probability that, he is, it's a girl. So if you want to know at least one is a girl, you need to subtract it from 100%. So for us, it's probability that is a girl, okay, girl. You need to subtract it from 100%. So you need to subtract it from 100% is 1/16. So probability that at least one is a girl. You need to subtract it probability that he's not a girl. So here is not a girl, that's not a girl. Okay. So that's probability is not a girl. So this is not a girl. So remember, not a girl. So meaning it's now probability it's a girl is subtracting the probability it's not a girl. So 1 minus this same denominator would be 16 minus 1 over 16. It's 15 over 16. That, if you convert it to decimal, it's 0.938. This is the probability that at least one of them is a girl. So the first thing is to find the probability it's not a girl. Okay, not a girl. 1 out of 2. 1 out of 2, it may not be a girl. Okay, so if it's not a girl, then we need to do it this way. That's the first examples. But for the second one, because they ask you, you need to assume that boys and girls are equally likely. Now, let's go with the second example exercise. Assuming that boys and girls are equally likely, find the probability, okay? Assuming that boys and girls are equally likely, find the probability of a couple having boy when the third child is born. Okay? So now, remember, third child is born. That's very simple. Well, assuming that you have a boy when third child is born, what's going to happen? Third child, only the third one. Okay, B, third child. What's the probability of having a boy on the third child? Yeah, if you have I mean, at birth, someone may be born male or female, but the third child can be boy. It's 1 out of 2. It's only one time, so it's 0.5. So that would be the probability of a couple having a boy when the third child is born. Given that the first 2 children were girls. Okay, so that means, we already know the only chance to have a boy on the third one is 1 out of 2 because we already know the first 2 are girls, so we don't need to fight for it. Let's do another one very quick. In this one, it is asked, in the United States, the true probability of a baby being a boy is 0.55112. That means 51.2% based on the data available at this written. So for a family having 3 children, what is the probability that the first child is a girl? Okay, remember, it's probability the first child is a girl equal 1 minus probability first child not a girl. So what is the probability child not a girl? It's 0.512. So meaning it's 1 minus 0.512. So we answer the first questions. That would be 0.488. So this is the answer. For B, the probability that all 3 children are boys. So what happened? The first child, all boys. What is the probability the first one is boys? Yes, 0.512. What is the probability the second one is boy? 0.512. What is the probability the third one is boy? 0.512. It's already given. Now, when you multiply all these 3 together, it gives you 0.134 or 13.4%. That's the probability all 3 children are boys. Now, what they ask you to do next, the probability that all 3 are girls. But we already know what's the probability they are girls. What is the probability of girls? All 3 girls. All girls. We need to know what's the probability at least one of them is girls. So it's 0.488. The second one is girl is 0.488. The third one is girls is 0.488. So when you said that, you multiply all these 3 together, it gives you 0.116. 11.6% that the second, all three children are girls. Next question is the probability that at least one of the children is a girl. So at least one of them is a girl. So first of all, at least one of them is girl. So you need to take the at least one is a girl. All you need to do is subtract from one probability that the first one is boys times probability the second one is boy times the probability the third one is boys. So after you do that, remember answer would be 1 minus 0.512 power 2. When you do that, you'll find the probability that at least one of the children is a girl is 0.866, or we can say it's 86.6%. Okay, so that's very important. Very important. So we're gonna go like this and focus and answering the questions. Okay, very giantly important. Now, for the third one, as you can see, it's a third exercise. I believe that's something you're gonna be doing. It's the same exactly as number two. I would definitely leave you number two to enjoy on your own. We're going to focus because, as I said, I do one, you do one, I do two, you do two. It's exactly the same type of questions, and you practice and let me know how do you do with these exercises so far. So that's very important to check. Let's go with number four. With number four, we said if you make, okay, we're gonna go with this one very quick, as we said. If you make random guess for 10 multiple choice SAT test questions, each with five possible answers, what is the probability of getting at least one correct? If these questions are part of a practice test and an instructor says that you must get at least one correct answer before continuing, is there a good chance you will continue? So the first thing to do, you know what? I'm going to copy paste and show that we're working with the only one exercise. So I have enough space. I erase on the first one, so I know what we do. Okay, let's do it. We're gonna go with green. Yeah, we are given what they tell us here, 10 multiple choice SAT tests. Each question has five answers. Only one is correct. So, correct answer, one out of five, right? One out of five is correct. You guess randomly on each question. Remember, it's not like something, you're gonna randomly guess on each question. And you want to find the probability of getting at least one correct question for the 10. So, and of course, they ask you to determine if it's likely you would be able to continue based on the instructor's rule, getting at least one right. So the first thing to do, you know, what is the probability of getting correct answer? Okay, correct. What is the probability of getting correct answer? Yes, probability correct answer. Correct answer. We're gonna say probability. I'm gonna call probability correct answer A. Okay. Incorrect answer. I'm gonna call it B. So probability of getting correct answer, how would you gonna call it? Okay, let's A be correct answer. Let's be incorrect answer. What's probability of A? Yes, one out of five. And what is the probability of getting incorrect answer? So we need to know what is the probability of B. Or we can say not A. Incorrect answer. Sorry, I'm gonna call it not A. So you can already guess incorrect answer would be 4 out of 5. So this one would be zero point 0.2 if you convert it to decimal and 0.8. 80% of the time you can get an incorrect answer. 20% of the time you get a correct answer. Now, if we use the complement rules, if you try to calculate the probability of getting at least one correct answer out of these 10 questions. So these complement rules, we need to do probability of getting at least one correct answer. How would you find that probability? Yes, at least one correct answer is the probability of getting no correct answer, right? No correct answer. So you can do that like this. At least one correct answer. You can say it's a probability of getting no correct answer. So probability of getting, now what we do, uh, you know, if you get no correct answer, what that for 10 questions, how would you do it? The first questions, no correct answer. The second question, no correct answer. If you do it for 10 of them, you can do 1 minus 0.8 10 times. You can say just power 10 if you want. So it's the same thing. Then, at this point, probability, because you do probability of getting no correct answer in the first questions is zero point 0.8 times zero point 0.8 times zero point 0.8 times zero point 0.8 times zero point 0.8. So answer here would be 1 minus whatever we find. Okay, so I believe maybe it should be 0.74, and at least of one correct answer is 0.8926, which is 89.26%. Okay, so probability of getting at least one correct answer, all right, is 89%. I don't know if you see what it is. First of all, we need to identify correct answer is 1 out of 5.2%. Probability of getting incorrect answer in one question is 4 out of 5, so 80%. So because you have 10 questions, you need to multiply 8.8 by itself 10 times. Then if you subtract it from 1, from 100%. So the probability of getting at least one correct answer is approximately 0.8926 or 89.26%. So that's a probability. So for us, since at this point, there is, because they said, the question said, if these questions are part of a practice test and an instructor says that you must get at least one correct answer before continue, is there a good chance you would continue? Right? Of course, yes. Look, there's a 89.26% chance of getting at least one correct answer by guessing randomly. So there's a very, very good chance you will meet the instructor's requirement and be able to continue. So yes, definitely, you can continue taking the test based on this rule, because 89% is like almost 90% of the time you get a good answer. Now, Now that you see this, I can also do another one, or I might leave it for you because it's exactly the same if we go with the next one, the other exercise, because this one is pretty similar also. Because what we ask you to do in the United States of America, 31% of world crash deaths involve alcohol. Based on the data from Global Status Report on road safety, remember, probability that, crash deaths, probability crash deaths involve alcohol. Let's say probability alcohol. I'm gonna just put alcohol, right? Alcohol is what? 31%. So 0.31, right? What is the probability? Because if no alcohol and crash involves no alcohol. You know what? Let's make it simple because I don't like to complicate things. I would say alcohol. I'm gonna use it A, no alcohol. I'm going to call it not A. So this one, probability of A is 0.31. What is the probability of not A? Yes, it's 1 minus 0.31. So probability of not A would be 0.69, right? So we're gonna keep it 0.69 for now because it's make it much easier for me to verify. Okay, now that you know this, okay, we want the probability that at least one of five, because what is the probability that among five randomly select word crash deaths, at least one involve alcohol, right? So we're gonna do exactly the same we did before. So probability that at least. Okay, that's what we're looking for. We want to the probability that at least one of the five randomly select word death crash involve alcohol. So if we use complement rules, we can go very easy on probability at least one. At least one of five, okay, randomly select or when involve alcohol deaths involve alcohol. So that would be one minus probability. It doesn't involve alcohol. What is the probability? It doesn't involve alcohol, right? It is one minus. Now remember, we said five deaths because we know that should be five. So it's the first one, 0.69 times. It's a five times. I can do power five. So that should be one minus a number. 1 minus 0.169, 169 maybe. Let's verify in my calculator what the answer would be. You know, 1.69. Actually, probability that is involved alcohol. What is the probability that among five randomly selected crash? What is the probability that among at least one involve alcohol? So we need to remove the probability of at least one of them involve alcohol, so which we did, right? And then we believe for that one, answer would be point 0.8, correct me if I'm wrong, 844. I think the final answer would be 0.844, that would be the answer. So the researcher can be reasonably, because they said if a researcher plans to conduct an in-depth study of road crash deaths that involve alcohol, can she be reasonably confident that the five road crash deaths will include at least one that involve alcohol? 84%. 84% of the time, right? So we can be certain, can be reasonably confident, because there is an 84.4% chance that at least one of the five deaths will involve alcohol. So what we can do, we know, the researcher can be reasonably confident that the five would crash deaths will include at least one alcohol, one and that involve alcohol. So don't drink and drive. That's the best thing to do, because uh, it's not guaranteed. It's only likelihood and maybe acceptable that initial research purposes, so you don't drive at all. That's for more insurance. I believe increasing the sample size slightly could further raise that confidence. Because remember, we don't they don't with five is not enough, so we can to use more a better sample like 30 or 50 or 100 to make sure it's working the way we want it. Now, conditional probability, let's talk about it. Very important to address the conditional probability. We now consider the principle that the probability of an event is often, affected by knowledge that some other event has occurred, right? So a conditional probability of an event is a probability obtained with the additional information that some other events has already occurred. I will buy you pizza given that Patriots win. So Patriots wins, I buy you pizza. The reason why I buy you pizza is because I already know it's conditional. So we write it at a certain point. If you have event A and B, for event A and B, you can write it event A given, event B given A, probability of B given A. That's how you can read it. All right, so let's see it closer. We said that's the notation, probability of B given A, or you can also write the probability of A given B. That denotes the conditional probability of event B occurring given that A has already occurred. So that's something we need to verify as well. We know it's important, we can verify it that this way. So probability that it's happened this way. Okay? Very giantly important. We call it conditional uh, probability. Okay? So let's do it. Um, we have the next one. Is that an examples? No. Intuitive, we're talking about intuitive approach for finding probability of A given B. Remember, we said probability of A given B. Okay? Prob of A given B. That means B occurred. That's why you can do A, or you can say probability of B given A, right? So probability of B given A. So remember we said denotes the conditional probability of event B occurring given that the other one has already occurred, right? So we know that already, and we can verify it. All right. So that's something you can verify of all time. Two events, you can use uh, this. Now, this is what happened. The We said here that the conditional probability of B occurring given that A has already occurred can be found by assuming that even A has occurred and then calculating the probability that even B occurs. So we have a formula that we can use. We've been using formula. So the probability of B given A can be found by dividing the probability of event A and B, both occurring by the probability of event A. All right, so we have this formula. It all depends on what you want to do. Probability of A given B. Remember, you can do that also. It's probability of A and B over the probability of B. You can do that also. Remember, we divide by the probability of the second element, the one we know. Okay, that's very important. In some of the books, how do you see it? You can see it. Remember, probability of A and B. In some books, you said probability of A intersect B over probability of A, or they can do probability of A. Okay, I try. A intersect B is probability of B. What you need to remember in this case also, A and B or B and A is the same because you only take the intersection of these two. Let's go with a few examples very quick. Uh, what I would suggest to do, remember in a previous video, I told you about this tables. We call it contingency tables. What I'm going to do, I will redo the question so I have enough space for it. Let's do, what is the font? It's 18. Let's do it 14. Hopefully you still can read it because I need to make sure that we can do the totals here. So remember, contingency tables, you must add a row total. Oh no, can I do a straight line, please? Can someone help me with a very straight line? I add a row and I do a colon total. Now you add 27 to 16. So take your calculator, grab your calculator, and let me know when you add 27 to 16. I believe it gives you 43. 12 to 34 give you 46. Now we're done with the row. Let's go with the column. 27 plus 12 give you 39. And 16 plus 34 give you 50. Now, if you add the total row, total columns, it must be the same. Total is 89. So always remember contingency tables. You need to, if the totals for rows and columns are not given, you must include them. That's very giantly important. Okay, so let's see what they ask us to do in these examples because we're gonna answer a few questions here. They said, remember we're doing some conditional probability. In these examples, they ask you, it's like the domination effect we're gonna do. So find the probability of randomly select a student who spent the money. Which one? Because they said, use the data in the following table in an experiment to study the effects of using 4 quarters versus $1 bill. Some college students were given 4 quarters and others were given $1 bill. And they could either keep the money or spend it on gums. The reason I summarize in the tables because that's what we do. Remember, the idea is to show you when you have coins in your hands, you feel like you don't have a lot of money. But if you have paper, even though they are equivalent, you consider it's money. So 4 quarters is $1, and $1 is also $1 bill is also $1. But the one with $1 feel like they have more money than the one with the 4 quarters. They're gonna show you in this table. It show you exactly if you have students given 4 quarters. We're gonna see if they spend the money to buy gums. Find a probability that a randomly select student will spend the money, I mean, buy gums, okay? Given that, you know what? How about we put in a letter? Let's put a letter. We're gonna call this one A. We're gonna call this one B. We're gonna call this one G. No, no, let's put letters that we would understand better. Quarters, I'm gonna put a Q. Bill, $1 bill, I'm gonna put a B. Gums, we're gonna set G. And M, I'm gonna try to avoid putting it there. So remember, given that, find the probability of G, given that the student was given 4 quarters, given that Q. So what you need to understand here, anytime you perform your divisions, okay, you spend the money, that means buying gums, given that you were given quarters. So first of all, you need to know by which total to divide. Whatever is given that's already the one occurred, you need to divide by that. So you divide by whatever is given. Given that the student were given 4 quarters. What is the total for 4 quarters? Yes, 43. So then you take the intersection of these two. This is the intersection of both like this. The intersection is right here. Now you can take the intersection is 27 over 43. Of course, you can also express it in decimal or in fraction or in percentages. 0.628 that you can rewrite also as 62.8%. B, find the probability of randomly selecting a student who spend the money. No, that's not B. B, find the probability of randomly selecting a student who keep the money, the probability of M, keep the money, given that's the slash, the student was given 4 quarters. So that means given that Q. Again, as I said, the given that is always the one you use to divide. You need to divide by that, okay? Given that is the letters you use to divide. So, what you should divide by what again? Yes, 43 because that's the one you know. And given that we given that and what is the intersection between keep the money and this one. So of course it's 16. That's the intersection between these two. Then the 16 would be in there. That's a fraction you can simplify or you express it in terms of decimal 0.372 or we can say 37.2%. Now, the last question, so I mean the C, what do the preceding results suggest? So this is something, it's subjective. So you can tell us what you think about it because it appears that when students are given 4 quarters, they're more likely to spend the money than keep it. More likely to spend because spend the money is 60.6%. 62.8% keep the money 37. So actually more likely to spend than keep. That's for the quarter, right? Now we're gonna ask the same type of questions for we're gonna uh we're gonna we're gonna ask the same type of questions for D, E, F, but at this point we're gonna the questions would be about it would be about dollar bill. Find the probability of randomly select a student who spend the money. That's the probability of G, given that what? The student was given $1 bill. $1 bill, we call bill G. So we know we're going to divide by the total for bill because that's the one given. That means 46. And what is the intersection between spending and $1 bill again? Yes, it's 12. Of course, you can simplify by 2 because that would give you 6 over 23 if you want to leave it in fractions, or you can convert to decimal 0.261 or is 26.1%. Find the probability of randomly select students who keep the money, probability to keep the money, probability of keeping the money is M, given that the student was given $1 bill, B. Find the intersection. What is the intersection between these two? Yes, that's 34 over the total for the one given that. Given that is 46. Again, here you can simplify if you want to leave it in terms of in fraction or convert it to decimal 0.739 or 73.9%. So what do the preceding results say? What do you see? Yes, it appears that when students are given $1 bill, they are more likely to keep the money than spending it. And it's all the reality. Give someone $20 in coins and give someone $20 bills. So it's more likely to spend the $20 in coins and save the other money. So that's something you need to verify all the time. And that's how it's worked. It's only a few questions among so many we can see here. But we're going to conclude by talking about confusion of the inverse. So remember, when we said you can see probability of A given B is not equal to probability of B given A. If you want to see it from the previous examples, look, if I do probability of G given Q, the first one I did 27 over 43. Okay, so probability of G given A, we see is give you 62.8%. But if we do probability of Q given G, now first of all, because we said given G, we need to divide the total of G. What is total of G again? Gums, purchase gum? Yes, 39. We're not gonna divide by 43 anymore. Given probability of Q given G, so the intersection is 27. You see, we don't divide. I mean, the denominators are totally different. So for this one, we're going to do 27 divided by 39. So that would give us 69.2%. Two different ones, okay? So when we talk about confusion of inverse, that's what we refer to, okay? So in examples, probability of positive test result subjects, we cannot just flip them. So that's what we want to show you. So confusion of the inverse is to incorrectly think that probability of B given A and probability of A given B are equal, or to incorrectly use one value in place of the other. You cannot do that. You cannot do that, all right? So that's why you pay attention. Do not inverse it, okay? So make sure you read, you understand, all right? Pay attention to it. Let's do one more examples. In this one, again, what I'm going to do is move a little bit so I have enough space. Remember, these type of tables, you always need to have the row total and column total. Yeah, my line are very straight. I think you enjoy that. That's total. That's total. Okay. Now, when you do, in this case, when you add 15 to 42, it gives you 57. 32 plus 9 give you 41. 15 plus 32, 47. 42 plus 9, 51. Now, either you add row total or column totals, answer must be the same, is 98. Let's answer very quick these questions because I see I'm going to put them very small so we can see. If you want to do better, please, I'm going to make it 12. I know you may not be able to see it, but I need space because I want to make sure I can do 1, I can do 2, I can do 3. Yeah, I think it should be fine, right? I believe we have enough space. Maybe can that help? Okay. I think each of them has this little spat that we can use. Okay. Again, make it much easier to work with. Let's use some letters. Polygraph indicate that result that the subject lie. I'm going to say subject lie A. Okay. That's polygraph, right? Now, subject lie, I'm gonna put it here instead. L. Subject not lie, I'm gonna put L. Subject not lie, I'm gonna put L. Lie. I'm gonna put it L. Not lied. I'm gonna put it not L. So I'm trying to make enough space, all right, to write everything down. Lie did not lie. And then remember, subject lie, but we have the results, right? So positive results of positive results. So we're gonna say positive result, okay? Subject indicate, polygraph indicates that's positive, okay? Positive for this one, and negative result for that one. So positive and negative, okay? So that's very important to see positive and negative. We can see it, all right? Let's see it this way. Okay. All right. So, okay. We said that in the first question, find the probability of selecting a subject with a positive polygraph, probability of positive polygraph, given that the subject did not lie. Given that the subject did not lie. So positive result, given that the subject did not lie, because we said given that, the answer, the total for given that the subject did not lie, what is the L bar? The total? Yes, 47. Now, what is the intersection between the positive polygraph and subject in that line? Yes, it's 15. So we're gonna say 15 over 47. So take the intersection, all right? Positive results are given that the subject did not lie. So answer would be 0.319. Or we can say 31.9%. So I believe I have enough space. Then find the probability of selecting a subject with a positive polygraph test, given that the subject did not lie. Why is this particular case problematic for test subject? This is the probability of the polygraph making it appear that the subject lied when the subject did not lie. So the subject would be unfairly characterized as a liar, right? Because they didn't lie, but the polygraph says it's lie. So that's a big problem. Maybe there is a defection with the machine, right? So we strongly advise that they check it. Find the probability. Okay, find the probability. Uh, uh, for B, you say find the probability of selecting a subject with a negative polygraph. Okay, probability of selecting a subject with negative polygraph, given that the subject lie. I put L. You see, it's what when it's when. First of all, intersection between negative polygraph and subject lie is 9. You need to put that number on the top and divide by what? The total where it says given that the subject lied is 51. Awesome. So 4 over 51 is 0.76 or 17.6%. Again, the same questions. What would be an unfavorable consequences of this error? Remember, they said probability of selecting a subject with a negative polygraph. While you already know the subject lie, you want the polygraph to show negative, but you already know the subject lie. So in this case, the subject appears to be truthful when telling a lie. The subject would receive undeserved credibility, right? So that's not fair. Let's go with the next one. Find the probability. Find the probability. Find the positive predictive value for the test. Okay. Find the probability of predicted values for the test. Okay. Predictive values for the test. And that means it's positive. That is okay. Find the probability that a subject lie. Probability a subject lie, given that the polygraph indicate lying. That means it's positive, right? The candidate it's indicate lying, so that means positive, right? Again, always take the intersection between these. So what is the intersection between subject lie and positive polygraph? 42. Given that it's indicate the polygraph is positive, what is the total for positive? Polygraph is 57. Yes, you did it. Okay. 42 over 57, that's definitely 0.737 equal 73.7%. They said, does the result make the polygraph appear to be effective? Look what happened. We said you find the body that the subject, right? The person lie. And the polygraph also showed that person lie. So is that a good thing? Yeah, to be truthful, truly effective, the probability should be much higher. There is not sufficient evidence to conclude that the polygraph is effective because, like, it tells you the polygraph show positive and the subject lie. So both of them positive should be like 90 something, maybe 99.9% or 97%, right? From 95. Sorry about that. Now we know. Let's do the last one. Find the negative predictive value for the polygraph. That is, find the probability that the subject did not lie. I mean, probability L bar, given that the polygraph indicates that the subject did not lie. So that means negative. All right. So given that, so what is the intersection between these two? Yes, 32. Given that the polygraph is negative, what is the total for negative polygraph? Yes, 41. Intersection over the total for what is given that. And answer would be 0.78 0, so that's 78%. Again, here, look, do you feel like it's effective? Because the probability should be much higher also. There is not sufficient evidence to conclude that the polygraph is effective because subject did not lie, polygraph said the subject is not lying, so the probability should be much higher than 78, like, wow, like 20 is ineffective. It's not accurate for 22%. That's a lot. So hopefully you understand conditional probabilities, complement rules. In a different video, we're going to come back for counting principles. That's a very amazing section that we will come back to cover. In the meantime, if you have questions, do not hesitate to reach out. Take care.